Hello, so we're going to talk about section 1.2, which we're going to call propositional equivalences. So propositional equivalences is going to deal with sort of the logical structures that we started working on in section 1.1, and we're going to do some moderately interesting things with them. So your suggested exercises are going to be 23, 29, and 31, regardless of whether you're doing a 6th or 7th edition book. So, this is section 1.2 in the 6th edition, but if you're in the 7th edition, I'll just weasel this in here. If you're in the 7th edition, this is actually going to be section 1.3, same problem numbers though, problem numbers 23, 29, and 31. So if you're in the 7th edition, this is section 1.3. If you're in the 6th edition, which is the book that most of you should have, it's going to be section 1.2. Okay, so what I want to do is I want to give you just a few quick examples, and then I want to focus on the DeMorgan laws. So, this is just going to be some really basic stuff like tautology, contradiction. We're going to figure out what logical equivalence is, which I alluded to last time. And then the real big fish for this section is the DeMorgan laws, or DeMorgan's law, or DeMorgan's laws. There are a bunch of things called DeMorgan's laws, so we'll see. But first, let's do just a couple of examples. So depending on, I think this would have been section 1.2 in the 7th edition book, and this might have been the second half of section 1.1 in the 6th edition book. But let's just do some examples of propositions to sort of cement in what we did last time. So if I said P is the sky is blue, and if I said Q is my shoes are dry, then I could form P or Q, which would be the sky is blue, or my shoes are dry. I could also do something like P implies Q, and I'm going to be really careful here, and I'm going to say if the sky is blue, then my shoes are dry. Now we want to be really careful here because there are a bunch of different logically equivalent, I haven't defined logical equivalence yet, but there are a bunch of different ways to say this in English that don't look like that. And one of them is something like, the sky is blue if my shoes are dry. And there are a lot of different tunnels you can go down to sort of get confused and mess things up. So I'm going to avoid doing a lot of this sort of word play. If you were writing a paper on philosophy and you really needed to shuffle up your words to make sure that things weren't getting too repetitive, then you should learn a lot of different phrases for P implies Q. But for this class, just if then is plenty. Or the sky is blue implies my shoes are dry. We can be a little bit robotic in this class because we're not writing super long treatises in this tight logical language. So you can do this with all of the logical connectives we learned last time, including negation and XOR. But I want to just kind of move past that. So if you see a proposition as an English sentence, then you can combine the English sentences by combining propositions. So let's move on to tautologies. So a tautology is a proposition that is always true. So an example of a tautology is P or not P. Okay, this will always be true because if P is true, then this part of the OR is true. So the whole OR is true. If P is false, then this part of the OR is true. So the whole thing evaluates to true. Similar, but the opposite, a contradiction. So an against statement, contra against diction statement. Contradiction is a proposition that is always false. And an example of a contradiction is P and not P. So this can never be true, because if P is true, then not P is false. So we don't have that both parts are true. If P is false, then this thing's false, so we don't even have to look at not P. So this P and not P is then always false. We can say that P is logically equivalent to Q if and only if Q is a tautology. And we write P triple equals Q. So here, when I'm saying if P, if I'm writing this here, I'm using P, which might be itself a compound proposition, and Q, which might be itself a compound proposition. And what does this mean that this is a tautology? It means that regardless what truth value this takes, this will take the same truth value, and vice versa. So that means that this logical connective, the bidirectional implication, will always be true. If it's always true, then it's a tautology. So the main thing that I want to get to, sort of the big idea from this section, is what I'll call Theorem 1, DeMorgan laws, or DeMorgan's laws. So like I said, there are a bunch of different things called DeMorgan's laws. So this is one instance of a general principle that we'll see multiple times throughout the semester. And I'm going to call this part 1, not P and Q is logically equivalent to not P or not Q. Second, I'm going to say not P or Q is logically equivalent to not P and not Q. And let's prove this. Now, to prove number 1, I'm going to appeal to a truth table. And in order to do this, I want to make sure that I have everything organized. So we set up a truth table, I think, last time. And I'll set up another truth table, but we're going to have to make sure that we understand the sort of inputs and outputs of this truth table. So here's P and here's Q. Those are my inputs. I've got a better way to do this. Then I've got what? Actually, I'll just keep doing this. Then I've got not P and Q. Pretty line. Then I've got not P or not Q. And I need one more pretty line there. Now let's look at all of our possible inputs. Well, we could have that both P and Q are true. We could have true and false. We could have false and true, or we could have false and false. Now, let's evaluate this truth table. The way I'm going to evaluate this truth table is just piece by piece. So I'm going to break up this first output column. I'm going to break it up so that I have the and that I deal with first, and then my output is going to be this negation. So P and Q is only true when both of them are true, otherwise it's false. And if I negate this column, I get false, true, true, true. And this is going to be my answer column right here. That's my answer column for P and for not P and Q. Okay, now let's look at not P or not Q. Again, I'm going to separate this out, and this is going to be my final column. If I'm thinking about this as like a machine that takes inputs and spits out outputs, the output is going to come from the OR. Because it takes the P and the Q, it has to do something to the P, has to do something to the Q, and then it has to do something to the combination of the two. So this P gets negated, and so this P right here gets negated. So it was true, now it's false. It was true, now it's false. It was false, now it's true. It was false, now it's true. Same with this Q here. This Q is going to get negated. So it goes false, true, false, true. And now I need to do an OR of these two columns, right? So false or false is false. False or true is true. True or false is true. True or true is true. So this is my sort of answer column for the second expression that I'm evaluating. And what we notice is that these two answer columns agree. Twinsies. Okay, those are the same. So if P and Q have some set of truth values and I plug them into this, I'll get the same output as if I plug them into this. So this was a proof by truth table. I guess I should have said this is a proof of part 1. I recommend looking at truth tables, spending some time with them. To prove part 2, I want to just go into like the English sentences that we did before. So let's translate the left-hand side of part 2 into English. So the left-hand side, okay, which we often abbreviate LHS. The LHS is, in English, how would I say this? I mean, just in really stuck up, like snooty English, I would say it is not the case that what? That P or Q. It is not the case that either P or Q or both are true. Okay, right? So what is this? Well, if I, just for a second, if I cover up this part, let's cover up the negation. What's P or Q? P or Q is either P or Q or both are true. That's either P or Q or both are true, right? But now let's negate that. And if I negate that, I bring these back in. It is not the case. That's English for negation, right? It is not the case that whatever follows is to negate whatever follows. All right, that's a maybe a strange way to speak, but it should be understandable. So it is not the case that either P or Q or both are true. Okay, so that's, if I'm saying neither P can be true, nor Q can be true, nor both can be true, that's the same as saying, well, that's just the same as saying both are false. So both P and Q are false, right? We're just translating this into this one sort of stilted English sentence into maybe a slightly more concise English sentence. But what's a way to say both P and Q are false with symbols? Well, I just say P is false and Q is false, and that's exactly the RHS, which hopefully you can guess means right-hand side. And that concludes our proof. We just showed that the way that I interpret this in English is precisely the same as the way that I interpret this in English. And that is stronger than just saying, well, this side implies that side, or this side implies that side. What I'm saying is this is logically equivalent to this. So hopefully that made sense. Let me know if you have